Welcome everyone to the penultimate ECR seminar of at least this session. So today we have Nicola Bellomo from University of Texas at Austin, who's going to be talking about tracing the large-scale structure of the universe using gravitational waves. So take it away.
So first of all, thank you very much for inviting me. I'm very happy to give this seminar. And I would have really enjoyed to come and visit you in South Korea, but hopefully in the future. So today I'm going to present you like a big project that I started during my PhD, like already 3 years ago with some students, and that has developed into something bigger. And it is related to using gravitational waves as a cosmological tracer of the large-scale structure. So I don't think I need to convince anyone about the fact that the gravitational wave detection by the LIGO collaboration and soon CAGRA has really opened a new era in astronomy. And it has really changed our understanding of black hole physics, but not only that. So it's not strange that every LIGO data release, there are like some anomalous events, which really tells us that we don't really understand quite well stellar evolution. And already with, sorry, you can see the image, I guess. So, in any case, already with the first part of the O3 data release, we have dramatically increased the number of the detected events. And soon O3b is expected to release another order 30, 40 events. So we are starting to have quite of black holes, and not only looks like. And in particular, if you're interested in one binary neutron star merger, that really had a huge impact, and really show how like a gravitational waves detection and cosmology can work in synergy to accomplish the different goals. And one of the two results of this binary neutron star detection was, first of all, we could measure the velocity of the speed of gravitational wave with respect to the speed of light, and we found that the two matches to a very high degree. And this allowed us to rule out several modified gravity scenarios that predicted that the speed of gravitational waves was significantly different from the one of electromagnetic waves. And a second possible application has been providing an independent measurement of H0. Of course, with only one detection, the error bars are not competitive with other probes of H0. But still, like predictions say that with order 20 events, these error bars are going to shrink down and be competitive with other local measurements of the H0 constant. So we can start imagining what is going to happen in the near future, when we are going to have many more gravitational wave events from different sources, especially black hole events. And we can start realizing that with these gravitational wave events, we can start tracing the large-scale structure of our universe using gravitational radiation. And this procedure is going to be independent from the traditional electromagnetic one, and complementary. So very soon, we're going to have like many galaxy maps from a multitude of galaxy surveys. I'm listing some of them here, but I'm sure I'm forgetting many others. And they're gonna map our universe over a large redshift interval with a very high precision. And then from the gravitational wave side, we can hope to have low resolution gravitational wave maps. which can be either obtained from resolved events by the LIGO-Virgo collaboration. So you can imagine of taking every contours given by this collaboration and build a map with that. And it's going to be low resolution because the localization of these events, especially those without optical counterpart, is rather poor. Or we can hope to have a map of the stochastic gravitational wave background. And once we have these two maps, we can combine them and hope to extract a lot of information, which can ranges like from standard multi-tracer applications. So you take two tracers and you beat down your errors on your cosmological parameters. But apart from this, let's say, standard application, which is still interesting, by the way, you can hope to characterize the cosmological properties of gravitational waves. For instance, their formation channel. In the latest LIGO data release, there was the first evidence of multiple binary formation channels for black holes. And you can hope to characterize these binary formation scenarios even more by joining these two big fields. And then if you're interested in the stochastic gravitational wave background, you know that it is made by an astrophysical part given by binary black hole neutron star, and binary neutron star events from its cosmological counterpart, which can come from many different models. And then, for instance, other application involves constraining modified gravity scenarios and so on. And in this talk, I'm gonna talk of some unconventional application, which is determining the origin of these binary black holes events. So, of course, all of you know that black holes can be created at the end of the life of a very massive stars. But out there are also other theories that predicts that black holes can be created also in the first stages of the universe, in the life of the universe, during the radiation-dominated era. And these are called primordial black holes. And they don't come from traditional star evolution, because at that time there were basically no stars. So before saying how we can determine if the detected black holes are astrophysical or primordial, let me just go quickly through what are primordial black holes. So as I said, there are black holes that form between the end of inflation and Big Bang nucleosynthesis. Since they are not related to traditional stellar evolution, they can span a wide range of masses. And if you want to consider black holes that didn't evaporate by now, you can have black holes that are as light as 10 to the minus 17 solar masses to black holes that are as heavy as 10 to the 4 solar masses. So, and I mean, the majority of this mass range is not compatible at all with stellar evolution. And since, interesting fact is that these black holes have all the right cosmological property to be a good dark matter candidate. They are cold, in the sense non-relativistics, they are non-interacting, and they are there since the beginning of the universe. Especially by the time of CMB, they are already there. And one interesting fact is that the formation of this object is always linked to beyond the standard cosmological model physics. So if you have your vanilla lambda CDM, the easiest lambda CDM you can think of, you're never going to be able to generate these objects. So you can, the detection of a single object of these kinds is going to really open a field. And okay, and how they can be formed, like I'm going to show an example just of the first case in which they form because of the collapse of large overdensities in the primordial universe, much larger than those that are going to generate a large-scale structure as we know it. So one question is that have driven a lot of attention is, are these allowed as dark matter candidates? And when we talk about this, we typically are interested in this parameter that is called H, which you the energy density in primordial black holes over the energy density in dark matter. So FPBH equals 0 means they don't contribute to the dark matter, and the FPBH equal 1 means they are the totality of dark matter. And you can put constraint on this quantity on the base of the fact that being extended object, they have a much richer phenomenology than, let's say, standard particles. And if you look to the mass range I was mentioning before, -17 and 10 to the 4 solar masses, you can see that FPBH equal 1 is ruled out in almost the entire mass range. So it seems that they are not viable as dark matter candidates. However, like this business is quite murky, and if you have questions, we can talk it about later. But what my point is that I actually don't care, because as I said, even if we detect only one, we can learn something interesting about the first stages of the life of our universe that we can't probe in other possible ways. And in particular, if we assume that these objects form because of the collapse of large primordial overdensities, we can hope to connect these large overdensities to some non-traditional inflationary stage. And the larger mass range allows us to probe quite significant range of scales. So if you work out the details, you see that the mass of primordial black holes scales as the wave mode to the -2. So if with CMB and large scale structure, you can hope to probe, let's say, from K 10 to the -4 to 1 inverse megaparsec, which corresponds to 6 to 10 e-folds of the inflation. With primordial black holes, you can hope to probe from 10 to the 6 to 10 to the 16 inverse megaparsecs, which correspond to 20 e-folds of inflation. And as you know, you typically need 50, 60 e-folds of inflation. So primordial black holes allows you to cover like a significant amount of this minimum number of e-folds you need. And the interesting thing, and we have a paper on this, is that starting from your abundance that you can constrain, and we did, you can reconstruct the shape and the amplitude of the primordial power spectrum. So what this constraint on the primordial amplitude looks like. So here I'm showing like a plot in which on the x-axis I have the wave mode in measured in megaparsec, and on the y-axis I have the scale invariant power spectrum. So you see that we have from 10 to the -4 to 1, CMB produces a very tiny constraint on the primordial power spectrum at the level of 10 to the -9. And then we have almost no measurements. We have some measurement from spectral distortions. We have some inferred constraint from silt dumping, and Donkey work on that. We have a very, I have to be honest, very suspicious constraint coming from strongly lensed quasar light curves. And then that's that. And you can see that with primordial black holes, we can really put some constraints on a larger range of scales. I know it's not as strong as the one on the CMB, but this is what we have to live with. And you can see that this red band shows you where the maximum amplitude of the power spectrum should be in order to observe FPBH compatible with observation. So you see that there are 7 orders of magnitudes between the value we find at CMB scales. So if we observe one of them, then we know that we need some non-traditional stage during inflation that boosts the power spectrum from what we observe at large scale to what we need to observe a PVH. And why I continuously saying even one of them, because if you work the constraints not for the maximum FPVH allowed, but for FPVH corresponding of one primordial black holes in your universe, you find this blue band. You can see that it's really close to the red band because we are exponentially sensitive to the value of the primordial power spectrum. And that's why detecting one is a big deal. And you can see that if you have these large primordial perturbations, these perturbations are going to generate gravitational waves. And we can hope to probe these gravitational waves. And here you see that we are actually being able to detect them once SKA or LISA switch on. So we can have also independent confirmation that we have really detected primordial black holes. So back to our business. So I hope I convinced you that even one is interesting. So let's figure out how to detect them. Well, first of all, I'm gonna say what I think that everyone here already knows it. So that different objects traces the underlying dark matter distribution in different ways, and we typically refer to these parameters that tells us how object traces the underlying dark matter distribution as the bias parameter. And what we typically write is that our overdensity in gravitational waves is given by our overdensity in the matter times the bias. So when we deal with primordial black holes, or in general the black holes, we have three possible formation scenarios, three major formation scenarios. So in the first one, these binaries made by primordial black holes form in the late universe. And in particular, they form through dynamical capture. So two of these primordial black holes that made the dark matter passes very close to each other. They emit gravitational waves and they create a bound pair. And then they merge and we observe them. And this is referred as late-time primordial black holes binaries. Another possibility is that these binaries form already during the radiation domination era. So these objects are created, and as soon as they are created, they start to move around, and they can form binaries through the same mechanism. And in the third one, you have the traditional channel in which your star evolves and forms a black hole. So it turns out that these three channels are associated to very different bias parameters, because the binaries characteristic of this channel trace the dark matter distribution in very different ways. So in the first case of late time binaries, you have a bias, roughly speaking, which is below 1. And is typically of low mass halos, dark matter halos. And this is because to have this process of that dynamical capture, you need for the object to have a very small relative velocities. And this is more probable in low mass dark matter halos. On the other hand, if these binaries are formed in the early universe, you expect to trace the dark matter in the sense that you expect them to be everywhere, equally distributed everywhere, to end up in every kind of virialized structure. And finally, if you assume they comes from stellar evolution, you expect this object to live in galaxies or in environments with that have like some intense star formation activities. And these are typically associated with high mass halos that are have a typical bias like bigger than 1. These values of the bias are like some kind of reference, are not, but it's just to show the potential of the idea. So, of course, events are poorly localized, so you can't hope to decide on a one-to-one basis if the specific binary is made of primordial black holes or stellar black holes. What you want to do is to do a statistical analysis, to collect a large number of gravitational wave events, to build a schema, and then to analyze the statistical properties of that schema. And to give you an idea of what is like the best angular resolution of different combinations of detectors, you can see that even when we are going to build the Einstein telescope, the best resolution we can hope to achieve is around 2 degrees, which means that once you build your statistical observables, like the CLs, you can hope to arrive up to a maximum L of 100. To be compared, to give you an idea, well, you know, Planck goes to L equal 2000. And if you do some, I think Euclid for weak lensing doing the CLs arrives to L equal like few thousand. So it's a very limited range of multiples, but still we can learn things. So, and what we can do some kind of null test hypothesis, just to understand if we can separate the stellar scenario from the primordial scenarios. Now, to do that, we have to compute these statistical properties. And we have released like a code that does that, which is called multi-class, and it's in an extension of class. That allows you to work with different tracers. So instead of having the CLs of gravitational wave and gravitational wave, you can also have CLs of gravitational wave and galaxies. And the crucial point is that these codes allows you to take into account what are called projection effects. And projection effects are physical effects that manifest themselves especially at large scale. And to give you an idea of what they are, these projection effects encodes a series of characteristics of both your source and the propagation of your signal across a perturbed cosmological background. So, as you know, your objects are going to live in a galaxies. These galaxies are going to have some peculiar velocities, and with respect to the traditional Hubble expansion. And photons are gonna, or gravitational waves for what matters, are gonna travel along curved geodesics because of intervening lensing effect by other large-scale structure. And of course, everything happens in a context where you have this gravitational potential at large scale that also influences the propagation of your signal. And you really have to account for all these effects. And we have the two papers that present this code. This exactly showing what happens when you neglect this effect. So you're going to have errors both in your forecast. So you're not going to really understand whether you can measure a signal or not, but also at the level of the analysis. So if you are going to try in the future to analyze this data using this technique and you don't account for this effect, you're going to have also a systematic bias in your best fit parameters. And now that the code is public. So can we really do that? So, and the answer, like to our surprise, to be honest, is that you can. And you can see here on the left column, the two estimators that we use. So for different combinations of gravitational wave detectors and large-scale structure, well, galaxy surveys. So the first thing that you can see is that, in fact, both estimators give approximately the same results. So it is some kind of reliable. Then you can see that already with Einstein telescope and DAISY, the combination of Einstein telescope and DAISY, we are gonna start finding signal to noise ratio bigger than 1, which means that we are able to say that one scenario is correct while the other is not. And this, so especially the left-hand side plot, have a maximum multiple of 20. So if you look to where the average values is on the right column, is at a level of 20. So you see that you don't need this huge resolution, and with the existing gravitational wave detectors, this is more than achievable. The band in all the plots represent the uncertainties we have on this signal to noise ratio. We can be traced back to the uncertainties both in the observation time in which you collect your data and in the merger rate, which, to be fair, is something that has really changed during the past year at every LIGO data release. And if you want to see, like, this has been a very preliminary analysis, and if you want to see a more refined analysis, you can check this paper that came out from the student that did this in our group. It's called Giulio Scelfo, and the paper came out on Monday. It's on the archive, and he further developed this. But it still find the results that are like along these lines. So this is pretty cool. But then, to be honest, when you try to do this kind of analysis, there are like a lot of assumptions that you put into your model. And if you really hope to use this technique to infer whatsoever, like as I told you, there are many applications. And if you really hope to use it, you have to start moving towards realistic predictions. And this is what I've worked on during the past year. And the fact is that when we deal with gravitational waves, we really have what I call a multi-scale and cross-field problem. Because if you want to be in this business, you have to worry about a lot of different things which are not directly related to cosmology. So in particular, you have to understand what your sources are, where your sources live, their host, and what's the physics both of your sources and your host, how your host is embedded in your cosmological context, what is the gravitational wave signal you're going to observe, how this signal is going to propagate in your perturbed cosmological background, and how you are going to detect it. So you see, you have like really from gravitational wave. So you need inputs from the different fields, from numerical simulation that are going to tell you what the signal looks like, to cosmological simulation to say, okay, how the galaxies that host this kind of signal distribute in space, to cosmological analysis that tells you, okay, how is the signal propagates in your background. And the goal of this project is to give people like numerical tools to deal with these different aspects in a kind of robust way. So let me show you an example of what you're going to be able to do once these pieces of numerical tools are going to be public. First, okay. Worry about sources and hosts. And then you can ask yourself, okay, model for binary living matter halos. How many parameters do I need to describe this model? And the answer is, with the minimal model you can think of, you already have 14 parameters. So to describe your gravitational wave event in its completeness, you need 14 numbers. And each one of these numbers is going to be drawn from a PDF, basically. And that PDF sometimes it's nice, and sometimes it doesn't. So I'm gonna just go over what are these minimal parameters to give you like a flavor of what you need to know. And again, this is the basic setup. If you want to do something that is more realistic, you have to start increasing the number of parameters and the complexity of your calculation. So suppose that you want to know what really matters for this problem related to gravitational waves. So you need to know when your gravitational wave arrived on Earth, and this is going to become clear. To know when your merger event happened, so it's redshift. You have to know what was the delay time between the formation of your binary and your merger event. And as you can see, like this is of order mega years. And from this, you can hope to infer some formation redshift. And again, the two, the merger redshift PDF and the formation redshift PDFs looks similar, but there is some kind of uncertainty in the delay time that you have to account for. So in this model, they look similar, but you can play around. Once you know your formation redshift, you can constrain. Well, you can draw from another PDF what is your host mass, and then from this bunch of information, you can also compute your host mass at merger. And it is important to have these two values because the properties of your binary depends on the properties of your host at binary formation time, but the clustering properties of your signal, on the other hand, depends on the properties of your host at merger time. So you need to discriminate between these two. And then if you go to the source level, you see that you need this is more intuitive, that you need masses from both objects, spins from both objects. Here spin is taken as a one-dimensional parameters. In reality, it's three-dimensional parameters, but again, minimal model. You need two numbers to locate your source in the sky. In this framework, we use right ascension and declination, but you can think about other coordinates, depends on just on your reference system. Still two numbers you need. And you need to know the inclination of the binary with respect to your line of sight, and the polarization, which is a fourth angle that tells you the relative orientation between your gravitational waves and the arms of your detectors. Once you have these 14 numbers for I don't know, your 10,000 gravitational wave events, you can try to understand which of them are going to be detected by your detector network on Earth and which one will not. So detected events are going to end up in the analysis I showed you before, in which while the unresolved one are going to end up in the analysis, in a similar analysis that you can do where instead of resolved events, you have the stochastic gravitational wave background. So from your catalog, by computing a signal to noise ratio for each event and in each detector that you are going to include, you're going to decide which one ends in which category. And just to give you an idea, when you compute a signal to noise ratio, you're really doing some, let's say, integration over your frequency range characteristic of your observatories, of your gravitational wave strain, and over the noise of your instrument. And the strain depends on what are called antenna pattern, which are called F plus and F cross. and what are just the strain of the two polarization state of gravitational wave H plus and H cross. So H plus and H cross, you take them from your numerical relativity simulations, while F plus and F cross, you compute them by knowing where the position is in the sky with respect to the position of your detectors on Earth, which changes with time because Earth is rotating and moving around your solar system and so on. And once you have that, yeah, you can hope to, okay, 3 minutes. I'm gonna finish in time, I think. You can hope to compute, for instance, anisotropies of your stochastic gravitational wave background. And to give you an idea of why you need all this, I'm gonna show you the only equation of this talk, which gives you like the fluctuation on the stochastic gravitational wave background. And this is quite a messy formula, but I can give you like an intuition of what you're doing when you're computing this fluctuation. So you're integrating over your entire redshift range because, of course, in this stochastic gravitational wave background ends up all the events that arrives now on Earth that have been generated at different redshift. You're integrating over all the parameters that characterize your events. So the 14 parameters we talked before, each one of them with their PDF. And what you are gonna have, okay, so the main structure, and then you have the number of events per year with these parameters that happen at this redshift times their energy spectrum times this huge bracket in which you have these what are typically called source function, which are these d, v, psi, and phi, which are functions that encodes the cosmological information, and you typically compute them with some Boltzmann code like class or CAM. And these source functions are multiplied by some astrophysical functions that you compute from your catalog of gravitational wave events using all the machinery I described above. That that multiplies the source function, and are computed from the catalog. And yeah, so the first term is what we already showed before. It is this bias contribution, whereas the like second, third, and fourth line are what I called before projection effects, and there are these effects that encodes the fact that your host is moving with some peculiar velocities and that your signal propagates across a perturbed background. And these are very relevant, especially for the scales that we are interested in. And you can see this in this plot, in which we compare the signal obtained including these projection effects with respect to the signal you would have including only this bias term. The scales we are interested in doing this analysis, these projection effects can be as large as like 20–30%. And some of them have like a positive, some of them are negative. So you can, when you include all of them, and then you have the dash dot and dot dash line that includes only a subset of them. And the important take-home message is that you need to account for all of them if you hope to do some robust analysis. And along with tools that allows you to do the two, like generate a gravitational wave catalog and generate a compute signal to noise ratio for different detector networks, we're going to release another extension of class that allows you to compute the statistical properties of the anisotropy of the stochastic gravitational wave type. We call the class SGWB with a lot of fantasy. And hopefully everything is going to come out next month. So in conclusion, and I think I'm on time. So I hope I convince you that gravitational waves really are gives us a unique opportunity to test our universe in a completely new way. And there is some natural synergy between gravitational wave physics and cosmology. So this kind of analysis is be relevant. I show you like an example of how you can infer the statistical properties of these gravitational wave events and how you can hope to establish that they have an astrophysical origin just through a statistical analysis. And stay tuned because there already are like codes that allows you to do this kind of analysis for resolved gravitational wave events. And soon there are going to be other tools that allows you like to do the resolved event analysis with a better precision, and also to do the same kind of analysis with the stochastic gravitational wave background. So thanks for listening. Yeah. I don't see the chat, so I hope nobody has written anything.
Okay, well, thank you very much for a very nice talk. So if anybody has any questions, please feel free to ask.
I had one vague question, if that's okay. I was wondering, like, just is there any like rough time scale of how long we will have to wait until, like, say, a gravitational waves gives like comparable constraints to, say, Planck on H0?
Well, it really depends on how lucky we are, right? Because so the estimates I've seen tells you that you need, let's say, 20 of these events with optical counterpart to have an error bar that is comparable to the one you have for other local measurements.
Right.
And then the problem is that, so I think you have two problems, like the first one is that the gravitational wave signal from binary neutron stars is weaker than the one from black holes. So the effective volume that can be surveyed by your gravitational wave detectors is smaller for binary neutron star events than what it is for black holes. So you have some volume damping effect on the number of events you can see in your detectors to look for coincidences. So I don't have a number, but yes, these are the limiting factors, and which are going to improve because there are at least other two planned stages for LIGO and Virgo. So there is going to be an 04, there's going to be an 05, and in the 04 also Kagra will join. So you're gonna have you will have like a fourth detector, and in 05, if everything works, LIGO India is gonna join. So the more the detectors, the biggest the hope you have to see these signals. But I wouldn't say less than 10 years. So if I have to guess.
It's really cool. Thanks.
Okay, thank you. Does anybody else have a question? So I had a question just on the constraint on the power spectrum. You mentioned that the quasar constraint was a bit suspicious. Do you know why that is?
Yeah. So it's so first of all, look to the scale. This is 10 to the 6 inverse megaparsec. So it's so if you go to real space, this is like 1 parsec. And the procedure, so yeah, so you're putting constraints in on fluctuation of the scale of parsec, which are really nonlinear, right? And the technique they used relied on linear theory. So that's why, and they have constraints only at this scale, 10 to the 6. It's not a range of scales. They can put a constraint only on a specific scale, which is very nonlinear, using a methodology that relies on linear theory. So that's why, well, and to be honest, not only me. I'm not the only one who's suspicious about this. But when we did this work, we included that like for the sake of completeness, to say, okay, this is everything that is out there, and then you can believe it or not. And you can check the paper and have your own idea of whether to trust this result or not.
Okay, yeah, thank you. Yeah, I would say that that's, yeah, perhaps not the most trustworthy looking thing.
On let's say on a
yeah,
unrelated note, like I don't know if this paper has been accepted for publication, so it stays on the archive for quite a lot of time without being published. So it's I don't know the story behind this.
Okay, thank you. So any other questions from people? If not, then I think we can draw this to a close. So thank you very much once again for attending this and giving your talk. And thank you.
Thank you for inviting me.
No problem. And thank you everyone for attending, and we'll see you hopefully in 2 weeks.
So have a nice day, and I'm gonna have dinner.
Have a nice day.
Thanks. Bye.
Thanks. Bye.